Okay, here we go, folks. Right, so happy. What day is it? Tuesday, everybody. I can see. Catania. I've been to Catania. I'm just looking at the chat here. I seen. Always ask where people are coming in from. I once crashed a car in Catania. Luckily, it was a rental. Luckily, I got the full coverage for the insurance for that one. It wasn't too bad, just a bump in the bonnet. You guys drive crazy in Sicily. But yeah, that was a great holiday. Right, where else have we got? Actually, a lot of people in Liverpool or just over the water on the Wirral. Namibia, fantastic. Kentucky. Wow, okay, so we're all over the place today. Okay, so it's 5 past the hour now. Let's make a start. So thanks for joining me, everybody. My name is Rob Treharne. I am a lecturer in the School of Life Sciences at the University of Liverpool, and I'm not actually I'm not a biologist, right? I'm always very quick to tell people that when I meet them. I'm actually a physicist by training. Okay, so don't ask me any questions about biology. But what I do in life sciences is I teach all of the first year undergraduates the maths and the statistics and now the coding that they need to go on and do their degree. Okay, and the reason for this event, I also run another initiative across the university called HiPi. Some of you may have been to a couple of our events before. It's a kind of weird group that just likes coding. Okay, so we kind of took it upon ourselves a couple of years ago to just have these events where we try and encourage as many people to code as possible. Am I muted? I hope not. No, you should be.
I can hear you.
You can hear people. I can see a couple of people in the chat saying they can hear. Thanks for that. Right, you can hear now. Brilliant. Okay, so just a bit of background. We started this group where we just started having these big events on campus where people would come in and we'd just introduce them to code. Absolute beginners, no experience necessary. And of course, we haven't done one of those events for, a while now, over a year. So we did what everyone else was doing, was we moved online, and that allowed us to get a much broader and international audience, which is super exciting. But the one thing I keep getting asked about, because up until this point today, we've only really taught Python exclusively. But I actually teach R in my course at Liverpool. And the one thing I always get asked is, could you do the same, but could you do it for R? So this is kind of a prototype class today to see if this will work. I have no idea if I've got too much content, not enough, or what it's going to be like. But what you're essentially going to get today is a whistle-stop tour of what I introduce my first year undergraduates in their life science degrees. That's everything from genetics all the way to zoology with a few things in between. Okay, so lots of programs at Liverpool, about 400 students. I can just see a question there from Loveson. Yes, I'm actually streaming this to YouTube as well at the moment. So it'll be available to you immediately. In fact, immediately available to you now. I'll post the link shortly so you can get it. You can rewind it if you want. What we're going to try and do today, so I'm going to give you this document in a second in the chat. You'll be able to access that. I'm going to introduce you to R. So you may need to use R for whatever reason. So everything today is going to be in the context of data. So this is not, even though it's an introduction event, it's not a kind of fundamental semantics sort of description of R coding. I'm not going to just start by saying this is a variable, this is an object, this is a list or a vector, and I'm not going to do that. I'm actually going to start doing things relatively quickly and from a data perspective. So the most important thing I really want you all to be able to do at the end of today's session, it's a 2-hour session, we'll have a break in the middle, is I want you to be able to at least read a data set, do some manipulation of that data, plot something. Thanks for the YouTube post there. And then and that's it really. And there's a couple of exercises at the end. You can test your knowledge. And if you want any additional resources on how to learn R, please do ask. I haven't actually put any in here, but I will update the document at the end, so I can kind of signpost some more of a basic introduction to today. Okay. Right, so first things first is I'm going to give you the link to this document. How do I do that? Let's share it. Right, so I am going to share it with, click on that. How do I do that? Oh, there it is at the bottom, I couldn't see it. I'm going to copy this link, change to anyone with the link, copy that, and then I'm going to done there. I'm going to go over to the Zoom chat here and link to document, link to resources. I'll put that in the chat. Okay, so I've just posted that in the chat. If you click on that link, you should be able to see this document. You will, I think you might need to have a Google account before you view it. I'm not sure if that's true, but most people do, so I'm hoping you can get a hold of it. And this is going to be the entire resources for the next couple of hours. Okay. So here's my introduction. My aims and objectives are relatively simple. I'm going to get you to start writing our code as quickly as humanly possible. This is going to be interactive, so get your fingers warmed up. You're going to be doing some typing, or I encourage you to at least try and follow along. If you don't want to, if you want to just let it wash over you, that's fine too. Okay, you don't have to participate, but personally I feel it's best to try and get those fingers going at the same time. There's not going to be an awful lot of code that you have to type. They're going to be kind of one-line statements, but if you can do that as you go along, that would be fantastic. We're going to read some data, we're going to interrogate that data and manipulate it. We're going to do some very, very basic visualization. I'm talking about things like scatter plots, histograms, and box plots. We're going to do a little bit of statistics, so I'm going to calculate the average value, or the mean, the median, and the standard deviation of a couple of data sets. And I'm also going to actually start to do a bit of a statistical analysis on some of these data sets as well. And what I mean by that is I'm going to use R to actually test hypotheses that I create for my data set. So I might have a data set and I might say, well, I think this group is bigger than this group. Here's my hypothesis. Is that likely? What is the statistical significance of comparing those data sets? Can I accept or reject my hypotheses? This is all stuff that we do with our students. We do it over about 6 weeks, so you really are getting the whistle-stop tour today. Before we do any of that, I need to get you to at least run a line of R. Now, there are so many ways of doing this. I'm going to show you my favourite. The best way to do this, I feel, today is actually to use this document. So at the moment, the document that you're at, if you're looking at this page, this link, you shouldn't be able to edit any of it, I hope, okay? But if you want to create a version of it that you can actually edit and you can write cells, I'll use the word cell, I'll come back to that in a sec. You can click on File, you can click Save a Copy in Drive, and it should, give it a second, it should bring up a version of that document which you can actually edit. Okay, so you can follow this along and you can start typing stuff in here. Don't worry if you don't get to do all of that today. I'm going to give you the full completed document at the very end as well, so you'll have a complete set of notes, and all the code that I typed today is going to be in this document. If you get lost at all, you can always go back to this document. Okay, so there you are, created that. And what I can do here is at the very top, you've got these two buttons, code and text. If I click on the button that says code, maybe I'll zoom in a bit here. Ooh, give it a second to catch up with me. Then that will give me, oh, I've gone too big. Hold on. Zoom out a bit. Oh, didn't like that. Right, there you go. If I click on the word code, oh, it gives me this kind of thing here, this cell. And I can start typing code in here. And once it connects and initializes, it'll actually print out any code that you run. So what I did there is I click code to put a new, what we call cell, a new code cell in there, and I type this print hello world, and then I can either press the run button to the left of it here, or I can press, I think it's shift and enter. Let's do that again. Yeah, shift and enter or control and enter as a shortcut to compile that as well. So Mohammed is asking, he's saying it's the first time event for him. Does he need any prerequisite knowledge of R? I'm going to say no, but I'm going to caveat with the fact that this is quite a data-orientated session. But everything I'm showing you from this point onwards is something I would give my students to as an introduction to R. Okay, so the best way I feel you could follow along today is by using this document. This is called Google Colab. I use this mostly for Python. Python is my first language, and I had to learn R in order to teach it to my undergraduates. And I love Google Colab because it is an online web browser based way to write code very, very quickly. I don't really write big scripts of hundreds of lines of code. I only need to generate usually little snippets and figures and things like that. So I like this environment a lot. Loveson's asking, Mr. Robert, will the Colab link be available even after the session? Yes, it's yours forever. It won't change. So you can use it at that link. Another platform for compiling code, which you can use to compile R, is called Replit. So if you click on the link here, this is something I've recently discovered, and it's more of an IDE-based way of doing it. Again, through a web browser, so it means you haven't got to download or install something. You can start writing code really, really quickly. This is what it looks like. So I've created an R environment here. I don't really like the colour. It's this colour by default. I'm not very good with the contrast here, so I can't see this very well. So you might need to adjust this. But from here, I can actually start to do exactly the same thing. Print hello world. Shift and enter will compile it. Oh, control and enter actually. And there you are. Out it pops on the edge there. You can use it in exactly the same way we're going to use it today. All the commands that we write to Google Colab, you can write here. For example, let's have a list of X values. I'm going to use as an example. Don't worry about this command. 1, 2, let's do 10.1. And I'm going to do the sign of that. Plot X, Y. So if I run this as an example, the only difference between what we're going to do today is every time we create a figure or a chart in the Colab, it'll just pop out on the screen. But if you do it in Replit, it actually pops out as another file, a PDF. Give it a second. There you go. It spits it out as a PDF. That's really the only key difference. I'm going to stick to using my Google Colab today. So that's two ways. Another way of doing it is using RStudio. Now, most people use RStudio, to be honest. In fact, when people talk about R and RStudio, they use those two terms interchangeably, even though RStudio is technically the kind of editor you use to write the script, and R is the underlying compiler for the language. And it's great, it's very robust, it's free, that's the important thing. It's free, so you can download it. Now, the important thing is that you actually have to download two things. Firstly, you have to download R, the compiler, locally to your laptop or desktop or whatever. And then you have to actually go and download RStudio, which is kind of like the editor. Okay, so I've given you the links to do that if you want to do it. If you're thinking about teaching R and you've got a large number of students, my advice to you is don't do it this way. Don't get them to install RStudio, because they each have, every student has a different computer, and they're all configured slightly differently. Mac users are the bane of my life in the first week of October when I try and get them to install this, because it never works on a Mac first time. So I would really encourage you to use any of the other platforms here apart from RStudio. Now, don't let me discourage people from actually downloading in RStudio. It's great when it works. It's very fast. It's very robust. But if you're trying to get a large number of people to do the same thing at the same time, it might be better to use one of the online platforms, because they don't need to install anything and everyone's configuration is the same. Okay. The kind of happy go between the online and the local is the RStudio Cloud. So RStudio, thankfully, have recently released a web-based version of RStudio, which actually looks exactly the same as RStudio. It behaves the same, you can store packages the same, you can upload files, and that's great. In fact, I've used that for my teaching this last year. The only disadvantage of that is everyone can sign up for a free license. Let me repost the link here. The only disadvantage of the RStudio Cloud is you can only get 15 hours free per month, which, if you're getting serious about coding, isn't actually an awful lot. You know, I can do 15 hours in a couple of days sometimes, right? Okay, thanks to HW for reposting the Colab link there. Right, so that is how the 4 ways you can write and compile R. Now, I'm going to stick with the Colab today, but please feel free to mess around with the others. I really like Replit a lot. I think I might be using that much more in the future. I'm going to keep using the Colab today, though, simply because it allows me to have all of my notes here, my document here as well at the same time. Okay, right, so the first thing we're going to do today is we're going to use R to read some data. Okay, now this is probably the most useful thing that you're going to do with any coding language, in fact, especially if you're doing some STEM subject as a degree, or you're thinking about being a data scientist. You've got to get to grips with data. Okay, so this is primarily what I use it for, both my teaching and sort of in my research as well. So usually my day starts with a data set. So what we're going to do here is I am going to give you a data set. In fact, it's here. Let me take a look at this. So I'm going to follow that link. And I've actually put this data into a GitHub here. So all the data that we're going to use today is in here. The one I'm going to start with is this baby elephant CSV. Okay. So what I'd like to do is, here's the data. This is how it looks on GitHub. Okay. I've got 2 columns. One has a time measured in months. So that's month 0, 2, 4, 6, 8, so onwards. And then I've measured the weight of a baby elephant with respect to time. So my second column here is its weight in pounds. Ooh, what a horrible imperialistic unit. So we're going to get that data. Now, if you follow the link, I'll post the link to this in a second. From GitHub, you can get any data just by clicking on the raw button here. I'm going to show you a much easier way to do this in a second. And then if you see this page here, if you right click and save as, I'm going to put this on my desktop a second. It's a CSV file. I'm going to save that, and it's downloaded it, babyelephant.csv. Okay. I can then go back to my Colab, and what I can do here is, if you see on the left here, I've got my table of contents where I am now. I'm reading data. On the left, there's a little folder icon. If I click on that, and then connecting to event, right, it's just going to connect me here a second. There you go. And what I'd like to do is, if you see this icon here, I'd like to upload to session storage. I'm going to click on that, and then I'm going to find that baby elephant file. There he is. I'm going to open that. I don't think you need to take sole responsibility for the pounds and miles, John. I'm pretty sure that was our fault. You just didn't change it afterwards. So if you are an American, we also use miles in the UK as well. And until relatively recently, we use pound. In fact, I still measure my weight in stone and pounds. Okay. At least we've got metric currency, right? Although I think there are some in this country that might want to go back to shillings, right? Anyway, so I've got that data here. Here it is. It's in my Google Colab. I need to read that file in. Okay, this is the first line of R we're going to write. Here we go. So in this cell, you should be able to see this green text here. Anything with a hash in front of it is what we call a comment. So if you don't want R to run a particular line, if you put a hash in front of it, it won't compile. It won't do anything. But it's really, really useful for you to write a bit of notes along with the code. And actually, if you're going to be doing a lot of coding, you should really be commenting a lot. I'm terrible at doing this. My students hate me because I am hopeless at commenting code. But if you really want someone else to understand your code and what you've written, you should be commenting a lot. Okay. So the first thing I'm going to do is I'm going to read that. I've uploaded the file, downloaded it and uploaded it. I'm going to create what I call a data frame variable. Okay. And all that's going to look like, I'm going to call it df. Okay, I'm just going to call it df for now, for data frame. Okay, and then I'm going to use the less than sign followed by the hyphen. Now this is a very, very unique identifier in R. In fact, it's only used in R. If I was doing Python, I would write the equal sign right now. Okay, but in fact the equal sign will work in R. But in R, the convention when we're assigning anything to a variable, we use this combination of the left hyphen or less than and the hyphen. Okay, and then I'm going to use my first R function. Okay, and the function I'm going to use should be pretty self-explanatory. It's called read.csv. There you go. Now it's a function, right? So what that means is there is a pre-prepared body of code somewhere in my compiler, which when I call this function, it will read all that, it'll chuck in some parameters and it'll do something. Okay. In this case, I want it to read all of the contents of the file that I've just uploaded. So a function name is always followed by an open bracket. Okay, and you can see what Colab here has done is automatically closed it for me as well. And the word I'm going to write in here is actually, or what I'm going to write in here is actually going to be the file name of the file that I want to read. And I'm going to write that, but it's important that I use quotation marks. Okay, that is very, very, very important. So I'm going to use quotation marks, and then I'm going to type baby_elephant.csv. Oh, I didn't need to close that bracket. And then I'm going to hit, well, I'm going to press play to begin with. See what happens. Oh, it's done something. It doesn't look like it's done anything, right? But if I type df here at the bottom, that's basically telling Colab to print out everything that's in the data frame. So if I run this line again, there you go. It's done it. It's printed out all of the data. It doesn't look as neat and tidy as it did in the GitHub, but that's okay. We can tidy it up a bit later. But what's important, I've got those two columns, the time and the weight, and here are the values. Okay, so my data has been read. Now, the only real disadvantage of Colab is that if I were to close down this browser window right now, it would forget the file, it would lose the file. Okay, so this file that I've uploaded here is only available during the session that you're using it, which means if you wanted to run it again, you'd have to re-upload the file. That's not great, to be honest. So there's a really great thing that this read.csv function can do. Remember the GitHub raw file I had here? What I can do is, if I just take that URL and I copy it, and I'd replace everything in the brackets with the URL. Oh, it's still got to be in quotation marks, that's important. And I run that again, it will actually read that straight from the URL, which is really, 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 really useful. It means I haven't got to keep uploading files. And if I come across any data in CSV format on the internet, I can just get the URL and read it. Okay, so that's a little trick there that we're going to use a couple of times in this session today. Right, so I've read the data. Fantastic. The next thing I want to do is I want to have a look. I want to have a look at the data. I've done that. Maybe I want to do some other things to that data. Maybe I want to sort it, or maybe I want to calculate something or create a new column. Okay, so a couple of things I want to do first. Now I'm going to cheat because I've got some notes here. I'm going to make sure I'm doing this right. What I'd like to do first is, okay, I'm going to inspect the data first. Let's put a code in here. There's a couple of things we can do, and I advise you to do this for any new data that you read. First, I'm going to type names, open brackets, df. So I've used the function names, and I've used it on the df data frame. And what that's going to do, it's going to print out the column names. So that's really, really useful. If you've got a large file with lots of column names, then you can always just see what the column names are called. I can, if you've got a massive file and you don't want R to print out everything in the file, you just want to see maybe the top 10 rows, if you do head and then open brackets df, comma, 10, control and enter, it'll print out the first 10 rows. Quite useful, including the column headers. Okay, or if you want to see the bottom, you can type tail, and it'll print out the bottom 10 rows. Okay, fantastic. What else can we do here? Well, we can determine the dimension of the data set. If I type, I think, dim df, this should spit out just two numbers. Yeah, so it's spit out 18 and 2. So it's got 18 values in the data frame, 18 rows, sorry, and 2 columns. And that's really, really useful if you've got a massive, massive data set and you just want to see how many rows are in it. You can type dim for dimension. Okay. Right, so what else can we do? We could sort the data. Let's have a go at that, right? So this data doesn't really need to be sorted because it is already written, it's already stored in a way according to how I've measured it in months. So I've gone 0, I think it's 0, 2, 4, 6, 8, 10. I'm measuring it every 2 months. I'm measuring the weight of this baby elephant in order. But you might have a data set which is completely unsorted and you want to sort it. So I'm just going to show you, if I want to sort the weight of my elephant in reverse. So let's say instead of going from an increasing weight, I want to do it backwards. I can do this, right? I'm going to do df, open square bracket. It's our first square bracket. That's exciting, isn't it, right? So I'm going to use a square bracket this time. And I'm going to type order. And that's a function, so I'm going to open up a normal bracket after the end of it. Now this is where it gets a bit messy. I'm going to type df again, right? And what I want to do here is I specifically want to target the weight column in my data frame. So to do that, I'm going to use a $sign, okay? And you can see as soon as I do that in Colab, it pops up with two options. I got the time in the month, and I got the weight in pounds. From my data frame. So Colab has found the columns and it's given me those options. I'm going to click weight in pounds, and I want to order that with decreasing equals true. So what that means, so by default, decreasing is equal to false, okay, which means sort of, if you think about it backwards, it's going to, the values are going to increase, okay. So I want to actually sort it backwards. Now there's one last thing which really it always throws me, and I don't know why this is. I'm sure someone can tell me this. But if you're using a function like this or statement like this, where you've got a function in the square brackets, you need to put a comma at the end of it. And now I'm sure there's a very, very good reason for that, but I've forgotten what it is. Okay, maybe we can Google that one later. If you don't do that, you're going to get an error. In fact, I'll get the error. There you go. I got an error in that, and it says it's got an undefined column selected. Okay, but I've typed everything right. The only thing I missed out there is a comma. And there you go. This time it's done it backwards. So you can see here, I've got the month starting at the 34 month, and I'm going backwards there with the biggest value of the weight first, decreasing. Okay, right. Sorry, I can see Chris in the chat there. I'm really sorry, Chris. I was meant to introduce you and I forgot. That's pure vanity, isn't it? It's just, what an ego trip. I forgot to introduce my colleague, Dr. Chris Mitchell. Chris is here. Chris actually teaches in the second year. So he does some really advanced stuff with some really cool data sets in R. And I'm really happy you're here today, Chris, and that you're answering questions. Please say hello if you can.
Yeah, I'm here. Hello, everyone. Yeah, just had some questions in the chat that I'm trying to pop in now. So if Rob is going through it on the screen and you have some questions, I'll try and get to them as soon as I can in the chat.
Forgive me for not introducing you, Chris. That was very rude of me, okay?
Oh, don't worry about it.
Okay, right. Yeah, so it's nice to know that you're there, Chris. Thanks. If you've got any questions, post them in the chat. Hopefully Chris can answer them. Okay, right, so we've ordered that. So that's how you might want to... I'm not really going to do any more with the ordering today. I'm not really going to use it beyond that, I think. Right. The one that's super useful is creating a new column. So you and I know, right, as scientists, that we probably should be using SI units for our weights, okay? Measuring things in pounds isn't useful, especially if you're a European, maybe in America, but you probably want to measure this in kilos, okay? Or if you've got measurements in pounds, you probably want to convert them to kilos, right? So what I'd like to do is create a third column on my data set here, which has all of the weight values, but in kilos instead of pounds. Okay, that's really, really easy to do in R. So I'm going to type df, which is, of course, is the name I've given to my data frame. I'm going to type at the $, and I'm going to type weight underscore kilogram. So that's a completely new column header. I haven't used that yet. Now I've used the underscore there. Instead of a space. If I try and use a space here, something's going to go wrong. Generally speaking, coding languages do not like spaces in their variable names, okay? There are a couple of exceptions. I won't go into those. And what I'd like to do here is I'm going to assign to that, I'm going to take the column of data for the weight in pounds, which I know exists, and I need to multiply this by some conversion factor, okay? So I know 1 pound is equal to 0.453592. That's probably too many significant figures there. Kilograms. So if I multiply it by this factor here, it should create another column with my weight in kilograms. Let's do that, okay? And let's just have an extra code cell here to make sure that that's worked. Boom. I've now got a third column which has the weight values in kilos. So that's super useful. Now if you're an avid Excel user, you know what you would have done there. You would have gone equals, click on that cell, times by 0.45 whatever, close the bracket, enter, and then fill it down, okay? And of course that probably would have taken you less time in Excel. I'm going to show you why we're using R and not Excel in a very short time. And hopefully it'll blow your minds, okay? But the next thing we probably want to do here, once we've got this data, once you've got any data, is to make a quick plot of something. There's nothing more intimidating than a massive data set the first thing we instinctively usually want to do is plot something to sort of eyeball the data. A picture's worth 1,000 words, of course, and that usually starts to tell us, what trends there might be in the data, where we should start, what questions we should be asking about the data. So visualizing your data is super important. And the first thing we're going to do to visualize the data is a simple scatter plot. I'm simply going to plot time against weight. Okay. Now that's really easy now. Now I'm not going to do anything fancy here. All the commands I'm going to use today are what we call native R. There are hundreds of thousands of packages that people have written to add into R. I'm going to try not to use any of them. I'm going to use one actually a bit later. There's a great plotting package which I know Chris uses a lot called ggplot. I'm going to have to do any of that today. That's not what this is about. But if you're really into making your visualization look really nice, you're probably not going to use the native commands I'm going to use today. You're going to use something like ggplot or something even more spectacular than that. So if you've got any questions about that, save those to the end, okay? I'm sure Chris can help out with that as well. Today, I'm just going to do plot. That's a function, so it's got to go in there. Now, that plot function takes two parameters. It's going to take the x values and it's going to take the y values, okay? So to get the x values, I'm just going to type df, and I'm going to do time month, comma, df, and I'm going to do weight in kilograms. Okay, there you go. And there it is, just pops up. Okay, so you can see here I've got a roughly linear increase in weight with time. And of course, this data is a complete fabrication. I've made it up, okay? I have no idea how much a baby elephant weighs. Actually, I think I did Google how much does a baby elephant weigh. But I think if it does put on weight, it's probably not going to put it on with such a neat linear relationship. Okay, so this is just for demonstrating how to plot something in R. Okay, what I've done here is I've committed a pretty serious cardinal sin here. Is I haven't really correctly labelled my axes here. So what I'm going to show you how to do is just, instead of what R does by default, is it takes the column titles and it uses those as labels for your axes. But really, you probably want to jazz those up a bit. So I'm going to do a comma after this, and then I'm actually going to hit enter, and I can bring it down. And then I'm going to type xlab, that's the x label, equals, I'm going to put weight, or baby elephant weight. Actually, I'm just going to type weight. Weight in kilograms. Kilo with a small k, don't forget. Otherwise, it's a Kelvin gram. Ylab equals, oh, I've done it wrong. That should be the y. The weight is on the y-axis. The x-axis is the time in months. Okay. And the last thing I'm going to do here as well is I'm going to use this parameter called main, and I'm going to give it a title as well. Weight increase of a baby elephant. Full stop. I'm going to hit Control and Enter, and it's going to make those changes. Okay. Brilliant. So I've now got correctly formatted X and Y labels. Okay. Usually, if a student comes to me with either missing axes labels or errors in it, I usually cry. Okay, that makes me very sad. So don't do that. Okay, right. Okay, the next thing we might want to do is we might want to actually draw a line of best fit on this graph. That would be a totally sensible thing to do, right? Okay, now that's a bit more involved, but it's still relatively straightforward. Of course, you could do this in Excel, right? I know you could do it in Excel. You could go add trend line, linear, and it would just spit it out. And you could even put the equation of the line on there as well. Okay, come on, let's do it in R. Right. So to do this in R, I am going to create a linear model. Okay, and I am going to use this function. Actually, I'm going to create a variable called linear model for the weight. Okay, and then I'm going to assign to that this function, LM, stands for linear model. And I'm going to do something a bit funky here. I'm going to give it the Y variable first. So I'm going to give it the weight in kilos. Right? Then I'm going to use this little tilde, the squiggly equal, it's like a squiggly hyphen. Yes, Zainab, I'm sure someone can post the link again. In fact, I'm quick enough, I can do it here. There you go. Then I'm going to put in the X variable, which of course is the time and month. Okay, then I'm going to put a comma. Okay, now at this moment in time, this function does not know what these labels correspond to. Okay, you actually have to chuck in a parameter called data equals, and then it's going to be my df data frame. Okay, and if I run that, should work. Okay, nothing's happened, but if I spit out my variable as well, here we go. It's called this linear model with this formula using this data, and it's giving me these two coefficients. Okay, the first one is the intercept, so that is the point at which a straight line, would hit the y-axis, and that is at about 36.92. Okay. And it actually says the word intercept, which is useful. This second coefficient is a little less informative, but it's actually referring to the gradient of that line. The gradient is 28.56, so that describes how steep that line is. Now it's a positive gradient, which is why the value is positive. But now I've got those two values. Those two values describe a straight line, y equals mx plus c. So I can then plot that line on my graph. Okay, and to do that, I'm going to go back up here. I'm going to copy this. Okay, I'm going to start a new cell. And I'm just going to do the same thing again. There it is. But this time, underneath where I've closed my plot, I'm going to type, let me remind myself, I'm going to type AB line, and I'm just going to throw in my linear model. Okay, LM, capital W, EIGHT, shift and enter, there you go. I've got a straight line on there. Okay, and what that line has done is it's tried to find the best fit it can by, I think it's a least squares method, if you're interested. Standard linear regression. Okay, Excel does the same thing. Okay, so if you can do all of this in Excel, including a line, you could probably even make it look a bit jazzier in Excel to a certain extent. Why are we bothering to learn how to do R in the first place? Well, I tell you what, not able to locate baby elephant CSV as showing in the screen. Okay, so I've got a question there from Loveson. He's having a bit of a problem with the data. So what I'm going to give you in the chat here, Loveson, is I'm going to give you the original link to the impact. I'm going to give you the link to the data. There you go. So if you do read.csv, open bracket, quotation mark, and then cut and paste that in there, and then close it, you should be able to read that data. Okay, let me go back to my Colab. Right, so I need to give you a reason to use R instead of Excel. Okay, now this is the thing. This is the question I get asked the most by my students. Why are we doing this when I got Excel? I can do it, and often that's completely justified, right? If you can do something quicker and faster using Excel, do it. Don't let anybody tell you, oh, you should be using code to do this. Don't feel put down if you're not using coding to do something you could do in Excel. I use Excel on a daily basis. In fact, some days I won't write a single line of code. I'll do it all in Excel. Use whatever tool is best for you. But if you're trying to do something which involves a lot of data and let me go back down. Let me scroll down to that line. And is really repetitive, then that sounds more like a coding task to me. Okay. Incidentally, I don't know if anyone followed this story in the news the other day. The other day, it was a couple of months ago now, when the UK lost about was it 18 or 80,000 positive test cases for COVID, because they were storing their entire database in a Microsoft Excel file, and someone, well, I wouldn't want to be this person, but they accidentally converted it to a .xls instead of a .xlxs file. And I think the .xls can only store about 64,000 records. So they lost a load of data because they were using Excel. So there are limits to what a spreadsheet can do. If you're using a CSV file, if they were using a CSV file, they could have stored as many lines as they wanted in there as possible. Probably they should have used more of a robust database, which I think they now do. So that was the story I like telling as a reason to use code instead of Excel. Okay, right. So we got too many elephants now. I'm gonna give you the data similar to that above, not for just one elephant, but for 1,000 elephants. And I'm going to ask, please can you tell me which elephant put weight on the quickest? Okay, now, you could do that with Excel. Thanks Hillary for posting that story. Brilliant, thank you. You could go through using Excel and you could make 1,000 plots. Good luck with that one. Or you could put your coding hat on and we could write a little loop that will go through each of those elephants in turn. It will calculate the linear model. You'll get that gradient, because it's the gradient I want. I want to know which elephant put on weight the fastest. So if I can get the highest value for the gradient, see which elephant that corresponds to, hey presto, I know. Right, so this bit is, it does involve a bit of coding semantics. I'm going to go very, very quickly, so if it doesn't make any sense, forgive me, we can talk about it at the end, but I just want to show you that you can do it. Okay, so what I'm going to do here is I've actually got another data set here. Here's the data. Let me click on that. Right, so this time you can see I've got the same columns, time in months, and in fact I've only got the weight in kilograms now. I've measured it directly in kilograms, and I've also got this third column which is called ID. So this is a code that I've given to every single elephant. I didn't think about naming every elephant. Okay, I've given them unique identifiers. So you can see here each of these codes are different. There's 1,000 elephants, so I've started off with all of the birth weights of the elephants. That's time 0. I had to scroll 1,000 places down to get to the first month, and I get back to this elephant's, where is he? 100822. Okay, so it's a massive file. I think it's not that big. It's probably about 50 kilobytes. But there's 1,000 times 18, right? So there's 1,800 records in that file. Let's read it. So I'm going to copy the URL. Remember what we did to read a file. Oh, hold on. There you go. Don't want to create a bookmark. We're going to read this. So I'm going to create a new variable. Let's call it elephants. And I'm going to assign to that read.csv, open quotation marks, paste that in, and then shift and enter. I've read that data. Okay. Let's have a quick check to see how many rows we've got in there. I've got elephants. There you go. I've got 18,000. I said 1,800. I meant 18,000 rows, right? Okay. And I got 3 columns. Brilliant. Okay. So what I want to do is I want to write something that's going to churn through this data. It's going to find every single elephant in turn. It's going to subset that data just to look at that elephant. It's going to get their gradient from the linear fit, and it's going to store that gradient value somewhere else. And then once it's done that for all of my elephants, I want to be able to say, right, which was the largest value and which elephant does that correspond to. Okay. So the first thing I really want to do here is I want to make a list of all of my elephants. Okay. I want a big list with all of those identifiers. And that's kind of difficult to do because each identifier excuse me, appears 18 times, okay? Because I've made 18 measurements on each elephant. So I would actually just like to get the 1000 elephant identifier. So to do that, I'm gonna create a variable called elephant IDs, IDS, and I'm going to use this function, unique. I'm going to call that column elephants, and that column is ID. Okay. If I do that, that's all good. Let me put that elephants, elephant IDS. If I run that, there you go. It's just spit out a massive list of all of those elephant IDs, and they're all unique. Okay, what's that there? It's a bit funky, isn't it? Right, so I've got my elephant lists. What I'm going to do next is I'm going to create another variable. Actually, it's going to be a vector, right? Called gradient or grad vals. I want the gradient value for every single elephant. Okay. And I'm initially going to define that as an empty vector or an empty list. If you use Python, they call it a list. You know, they call it a vector. I don't know why. Okay. So to do that, I use the C followed by an open and closed bracket. Okay. Okay, yeah, if you use colons, that's Python, okay? So that's an empty vector. I'm not going to start a new cell, I'm going to keep going. Now here's the funky bit, okay? I'm going to create a loop. I want to get through every single elephant one by one, right? So I'm going to do this. For, and it's gone blue. R knows what I'm about to do. It knows I'm about to type a loop. Then I'm going to open a bracket, and I'm going to say, let's do E in, excuse me everybody, elephant IDS. So what it's going to do, it's going to find each elephant IDS, or it's going to use this list of this vector above, and it's just going to iterate through it one by one. So it's going to start with an E value of my first elephant. I can't remember what that was. I'm going to open up a curly bracket at the end there, and I'm going to hit return. Okay, so everything within those curly brackets now represents stuff I want to do during one cycle of a loop. Okay. Oh yeah, sorry if I've cut stuff off here. Yeah. Then what I want to do is I want to take my whole data set, and then I want to subset that data so that I'm only looking at the elephant records with the ID that I'm currently looking at in my loop. Okay, so I'm going to create another data frame. I'm going to call it a DF, and I want to subset that. So subset is a function I use all the time in R, and what this function is going to do is going to allow me to look at my original data frame, that's elephants, okay, and it's going to allow me to use a conditional statement to filter out any rows that I don't want. Now I only want rows that have the ID value of the elephant that I'm currently looking at. Okay, so I'm going to type elephants. That's the data frame again. Hit it with a dollar sign, ID. So I've only got the ID column. Now I'm going to put a double equals, and it's got to be a double equal sign. That means it's identical to E, okay, which is the value of the elephant ID during this one cycle of the loop. Okay, so that'll create a new data frame called DF, which has only got records associated with a single elephant in. Now I've just got to do that fit again. So I'm going to create my linear fit using my LM. It's the same as the line I wrote earlier. Weight in kilograms and time in months. Now I think the mistake I've made here is in my data set with all of the elephants, I've used months plural instead of month. Okay, so be careful there. That's my fault if you get an error here. And then I'm going to call data, and the data frame I want to look at is only this subset here, df. Okay. I've got an error traced back there from, I think it's Hillary. I think you need quotation marks around your URL. Yes, you do. Yeah. Yeah. Thanks, Chris, for confirming. Where was I? Right, so I'm getting that fit out for every elephant in turn. And then what I want to do is I want to get the coefficient of, I want to get the gradient, and I want to add it to this list here. Okay, so I'm going to do that by doing this. Grad vals is equal to, or is assigned to, a vector which has all of the original grad vals in it. So at the moment, that's got nothing in there because I'm on my first elephant. And I also want to put my fit, and this last bit here, this $ coef, like you have to trust me on this one, 2 is, let me just explain what this is a second. Remember I had my lm weight above here. I did it for the first elephant, okay, and I gave me the time in the month which corresponds to the gradient. Okay, now that's great, but I only want this value. I only want to use this value. Okay, so to get that, I could type coef. Okay, that'll just give me the values of the intercept and the month, and I actually only want the second one, so I type square bracket 2, and that only gives me that gradient value. So that's what I've done here. I'm just appending this gradient value to my list of gradient values for every elephant. Okay. Okay, if I run this, in fact, if I output the gradient values as well, give it a second. So it's now cycling through every single elephant in that data frame. Oh, I've got an elephant. Elephant. Oh, I spelled elephant wrong. Doesn't help, does it? And now we're going to take a break. So there you are. It's got the gradient for every single elephant. 1,000 of them. So I've got to find the highest value there and then figure out which elephant that corresponds to. Okay. Right, so to get the highest value in grad vals, I have to do, in fact, let's start a new, get rid of that. Run that. To get the highest value in grad vals, I do max grad vals. Because the highest gradient is 36.86. Okay. But that doesn't tell me which elephant it corresponds to. So, in turn, I need to do. Let me figure this out. I need to do. Is it? Don't think that's going to work. Okay. Time and months. Okay, what is done here? If I type, okay, firstly, let's go through this again. The max grad vals gives me the maximum value, okay, of the gradient. So that basically tells me the fastest rate that an elephant put weight on, okay. If I want to get which value that corresponds to in my list, in other words, the index of the lists, if I type which dot, that tells me that in this list of IDs, it was the 891st elephant which had the highest gradients. Okay, so remember that value, 891, that's fantastic. So to then figure out which elephant that corresponds to, I have to do, I'm going to do elephants, I think it's 891. Nope. Oh, I got to define the column first. Elephant ID 891. There you go. So this is the ID of the elephant that I need. Well, that's put on the biggest weight. So 963251 is the elephant that has put on the most weight. It's not necessarily the fattest elephant. It's just the elephant that's put on weight the fastest. Okay. If I wanted to find the minimum, I could just do min. That will give me 663. And then this ID corresponds to the elephant that put the least, put weight on with the least speed. I've said elephant too many times now, right? Which means it's time to take a break. Right, so that was a bit grueling. Maybe I shouldn't have gone into too much detail there. This is probably not something I would do in a first year course, which was data orientated, but I really wanted to show you that you could do something useful with code that you can't do in Excel, or you can't do in Excel easily. Okay. Right. So we're going to take a break. Let's have a good 10-minute break. Right. Go get a glass of water. Maybe step outside into the sun. Sun's out, and then when we get back, we're going to. Let me just explain what we're going to do when we get back. We're actually going to look at a real data set. No more elephants, thank God. So we're actually going to look at the Breast Cancer Wisconsin diagnostic data set. Okay, so this is a publicly available data set used for machine learning. We're not going to do any machine learning, sadly, but we're going to use the data and try and do a bit of statistics on it. Okay, so have a 10-minute break, everyone, and I'll put the tunes back on for 10 minutes, and then I'll see you at, let's say it's 4:05 now, so I'll see you at 4:15. Okay. Brilliant. Thanks, folks. Okay, we're back. Right. Okay, so I should say sorry for that coughing I've been doing. I've had a cold. Thanks to the little one for that one. Right, we have just, what have we done? We've read a data set. We've done some jiggery pokery. We plotted a scatter plot. That was good, isn't it? And we did something that we probably feel only R can do instead of Excel. Let's now perhaps start to look at a real data set. Okay, so the best reason to learn any language, be it R, Python, JavaScript, whatever, is its application to real data sets. Okay, so this is the exciting bit for me. Okay, so we're going to look at the breast cancer Wisconsin data set. I'm going to click on the link. I'll show you what it looks like. It's an old data set. It's like 1995. Okay, how old was I in 1995? Not that old. Okay, 10. But it's a really good example of what a data set might look like, and what this data set contains is a series of measurements on, I can't remember, I think it was over 500 patients with tumours, breast cancer, and it contains a diagnosis as to whether those tumours are malignant or benign, and they made a whole series of measurements on those as well. I'll show you the data. So, but the reason we're doing this as well is because most data sets you're going to encounter aren't going to play nice. Not like the elephant data set, right, where you just got two columns. You might have data missing. You might have column headers missing. You might have columns where you have no idea what it corresponds to. And you might have to do a degree of tidying up before you actually start to use that data. Okay. This data set, if you want to get a hold of it, this whole page contains as much information as you're going to need on this data set. So it describes all of the acronyms used, got a link to publications, relevant publications. This is the useful bit. This is what they've called the attribute information. This is the column header information. So I've got columns 1, 2. That's an ID number. So that refers to a specific patient. And then a diagnosis, M for malignant, B for benign. Okay, so those really are your primary columns. Okay, and then you've got 10 subsequent columns with values that have been measured. So you've got the radius from the center points to the perimeter of the tumor, the texture, that's the standard deviation of grayscale value, so obviously they've taken that off an image by the looks of it. The perimeter, the area, smoothness, compactness, concavity, concave points, symmetry, fractal dimension. If you've ever studied fractals, you'll know what a coastline approximation is. It's been a while since I did that. It doesn't really mean anything in this context, actually. Or does it? We'll find out. Let's get the data. Let's go look at the data. Right, so here's the data folder. That looks promising, doesn't it? Let's go and take a look at that. Okay. Oh, good old Apache. Right, so we've got a load of stuff in here. Now, the one that I really want, the one that I found the most useful, is this wdbc.data file. Let's take a look at that. In fact, you click on it and it's going to download it. Okay, which is okay. I can save that where I want. But actually, what I might do is I might right-click, copy the link. Okay, so I've actually got the URL of that it's not a CSV file, it's a .data file, which is, as far as I'm concerned, is a made-up extension. Okay, or maybe an extension that was available in 1995 that isn't available today. Thankfully, R will still read that data as a CSV. I've checked. Okay, and that's often the case. R can often do stuff just intrinsically. So what we're going to do is we're going to right-click on that, copy the link address, and go back to my collab, and I'm gonna do let's do cancer data, and I'm going to do read.csv, and I'm going to paste that in. Okay. Okay. Right, it's done something. That's fantastic. Let's put another code cell in there. I'm just going to print up the data, right? Cancer data. Okay. And I'm just going to print the whole thing out. There it is. Wow. Okay. Ooh, that's a lot of data. Okay. So that's it. Now I can see something's not quite right here. Okay. Because these header titles don't mean anything. They don't mean anything to me whatsoever, right? In fact, it looks like the header is made up of information which should be an actual row. Now, what's happened here is the data is probably just solid data. It doesn't look like there are any header titles in this data set, which is why they've given them on the website. Okay, which is a pain, isn't it? So what we've got to do is, well, first we got to do two things. First, we've got to tell R not to interpret the first line of our data as header information. Okay. Now we do that using this additional parameter here. Let's do comma headers equals false. So I'm writing that in the same line, the same function I've used to read the data. Let's do that. Shift and enter. And if I show you, didn't like that. Why not? Let's figure it out. Figure that out, shall we? Header, not headers. Should have seen that one coming, shouldn't I? Header equals false. Let's read it. Let's spit it out again. Let's do head cancer data. Let's do the first 5 rows instead. Okay, there we go. And now as assigned default variable names to our headers, which is just put as v1, v2, v3, v4, v5, v6, so on and so forth. Okay. Right, now they've told us on the website, let's go back and take a look, that the column header titles correspond to these things. Okay, so what I would really want to do here is I want to relabel these variable names, these variables with the header titles. Okay, let me just change this. So what I'm going to do here is I'm going to do this. I shouldn't be names. It should be cancer data. Okay, now I've done this already. Okay, you have to change the name of this, I think, because I called it something else previously. I'm now calling it cancer data. That's my data frame. And what I've done is I've put a big listing here of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 header names, okay, which I've got from that website. And if I do that, okay, that's done. If I go back and run this head function, I've now got the column headers. Brilliant. I can work with this, right? Now you'll also notice I've got a load of other stuff here. Even though this said there's only 30, I think it says there's 12 columns which I've named. It looks like there's a lot more data in here. Now I don't know what that data is, frankly. I think it could possibly be repeat measurements, but I don't know. So I only really want to work with the data for which I know I've got explicit column headers. Okay, so what I'd like to do is I like to create a subset of this data, which is just the first 12 columns. Okay, so I'm going to create a new data frame, which I'm going to call cancer data subset. Right. Okay, question from Hillary. How did you name the tables as head cancer data? Okay, that's a good question. So I actually named it cancer data above here as it was hiding, look. So I used cancer data as a variable name, and then I used my read.csv function. Okay, so that has read all of that data into a data frame called cancer data. And then this head function is just saying, right, well, I only want the first 5 rows of the cancer data frame. Okay, I hope that makes sense here, Hillary. Okay, share the Colab link again. I can do that. There you go. Right, now I'm going to create this subset this time. So I've renamed all of the column headers using this information here. This is just a big long list. And then I'm going to create a new subset which is based on the original cancer data. That's the full data frame, but I'm going to cut this up. Okay, and to do that I'm going to use a square bracket, open a square bracket, and I only want the first 12 columns. So I'm going to do 1 colon 12. Right, the colon's important. That's telling R, excuse me, I got some water this time, hang on. That's telling R that you only want to pick out the first 12 columns from 1 to 12. Okay. If I do that, it's done. Trust me, it's done. All right. You could look. You could spit it up again. You can see there's only 12 columns, or you could do dim cancer data subset, and you can see it's got 569 patients, but only 12 columns. Okay. Right, it might not be 569 patients, but we'll assume there is. There could be more than one. There could be a patient with more than one tumor, okay, in there. So it could have multiple patients with the same ID, but there are 569 rows, okay. Okay, that's a good start, isn't it? So I've got a working data set. I've got a load of columns. I think the first thing I would like to do here is just get some summary statistics out of my data set. So I'm talking about the mean, the median, interquartile ranges, all the stuff you did when you were in school that you probably rolled your eyes at, but now you actually realize is quite important. Those measures of what we call central tendencies are critical in reporting any information about large data sets, right? When you read a newspaper, you don't see the data table, right? You get the mean or the median. So it's really, really important in communicating quickly what your data look like to others by quoting these values of central tendency, the mean essentially of the averages. Okay, and of course, depending on what context you're using, it might be more appropriate to quote the median. It might be more appropriate to quote the mean. You might want to quote that by group as well. So obviously you get the mean for all of the data, but you'd also have means for each of the groups of patients that had malignant or benign tumors as well. You can divide it up like that too. Okay, so what we're going to do is I'm just going to show you how to get those out. So let's get the mean tumor radius out. That's really, really easy. I'm going to type the word mean. That's a function in R. So I'm going to open up a bracket afterwards. I'm going to call my subset, that's cancer data subsets. And I want to know, I'm actually getting the mean of the radius column. So I'm going to actually type in, here are all my columns, I want the radius. Okay, if I run that line, my mean value is 14.12. Now, I haven't showed you this, but in that data set, it did say on that website that this value, the units are microns. Units are always important. And really, I should have included them in my header titles, but I couldn't be bothered. That's not a good example, is it? Always include your units, folks. It's really, really important. It's microns. Standard deviation. That's really simple as well. SD. Cancer data sets. Cancer data subsets. Radius. Okay. You could also do this. I'll do the same for the median. It's median. Whew, cancer data subsets, $, radius. Of course, I could have called any column I wanted here, okay? But I'm just looking at the radius for now. That should spit out these 3 values. That is the mean, that is the standard deviation, okay? And this is the median. So you'll notice that the median and the mean are slightly different. that's to be expected, okay? Okay, so that's really, really good. That allows us to get a handle on our data and use a single value to describe the kind of overall collection of data. That's what a mean is, right? Really, really useful. We can go a bit further here. We can generate tables of these summaries very, very quickly in R. But to do that, we're going to use a new package. Okay, time to get excited. Now this is, when I was talking about RStudio earlier and saying the kind of problems you run, this one caused me the biggest headache a couple of years ago. I'm going to install a package that exists but isn't sort of preloaded when you run RStudio, called Psych. And actually it's a package written by a group of psychologists, I think, I can't remember where they were, specifically for their own sort of statistical analysis of data sets. So the package is called Psych, P-S-Y-C-H, and I need to install this package before I use it, and then I need to actually load the package into my environment. So there's 2 lines of code I got to use here. One is install.packages. Now if you're using RStudio, you can do all of this using an actual graphical interface, not graphical. Yeah, I guess so. That's what a GUI is, right? So basically a point and click environment where you can search for that, install it by clicking a button. I'm going to do it the hardcore way. I'm going to type the line of code, okay? So I'm going to install that, and then I'm going to call this library psych. Notice the difference here. The psych in here doesn't have quotation marks around it, but if I'm installing it, I need the quotation marks. That's a slight inconsistency, which bothers me. You would never see that in Python. Okay, just saying. All right. Okay, so I'm going to hit that. I think I've already installed it, but it's going to do it again. If you're doing this for the first time, this might take a couple of minutes. In fact, it's thinking about it. Usually it gives you a bit of an output here as to what it's doing. You can see it's also installing a couple of other packages. So if you need to install something, and that package itself has additional packages that it depends on, R should install those automatically, okay? Oh yeah, thanks, Loveson. That's true. So if you've ever used Anaconda, which is a pretty hefty distribution, it used to be just Python. It's now got R with it, so that's great. If you were to install, if you wanted another way of installing RStudio, install Anaconda. That way you've got Python. I think that comes with PyCharm. I think that's right, and you'll have RStudio with R. Okay. Maybe we could post the link to that at the end. Someone remind me to do that. Okay. Right, I think it's installed, and what I want to do here is I've already created my subset that contains the first 12 columns, and then I'm going to use this function called describe, D-E-S-C-R-I-B-E. This function is explicitly referring to this psych package. If you try and run describe without installing psych first, no dice, it'll get an error, okay? All I'm going to do is I'm going to give it my data set, my data frame. So cancer data subsets, and I'm going to run that. Look what we got here, right? Isn't this beautiful? I've got a whole table according to what column I want to look at. So there's the radius, and it's calculated the mean, the standard deviation, the median. I've forgotten what trimmed is, the maximum value, the minimum value, the range, the skew. Skew and kurtosis refer to the shape of a normal distribution. You've also got the standard error in there. Oh, goodness gracious. So that is a really quick way of generating a lot of summary information very, very quickly. Super useful. You've also got this as a data frame. You could save that as an Excel spreadsheet. I forget how to do it. Oh, someone's going to ask me how to do that later. But you could generate a nice table based on that information, okay? So you've taken all of those records and you've calculated these central tendencies using this one line. That's really, really useful. You can do a bit more than that. Right, is it that simple, Chris? Write.xls. Yeah. I won't try and do it, but I believe you. Write.xls. Let's do it actually. See what happens. So if I create a variable, let's call it summary, and I instead, rather than just print it out, I create the summary, and then I'm gonna do write.xl. Oh yeah, XLS summary. Does it do it? Maybe it's SLSX. Am I doing this right, guys? Excuse me.
For write.xlsx, it's from a package xlsx.
Okay, so we'd have to do install packages xlsx.
Yeah.
I knew that was going to come.
But you can write a CSV file in pretty much the same way.
Okay. Yeah.
Specify the file in the function, and it will save a file.
So it'll be summary. Let's call it output.csv. That's what I forgot, didn't I? If I refresh, there it is. It's giving me a CSV file. Brilliant. So I could get data out of it as well. Thanks, Chris. Thanks for that. So I'm not going to install XLSX now, but it's nice to know that we can always get data out of whatever we're doing here. We can also do those summary statistics by group. Okay, so we've got these two groups according to whether the tumour was malignant or benign. So if you were to write describe by, put your data frame in, I'm going to have cancer data subset, and then I'm going to type that again, but I'm going to specifically group it according to that diagnosis column. If I do that, Control and Enter, that will actually give me two data frames. And it's not formatted as nicely. If I want each one of these data frames in turn, I can actually call them according to 1 or 2, right? But the first one refers explicitly to the benign group. Excuse me. And the second one, it's down here somewhere, refers to the malignant group. Okay, so you can actually group those summary statistics as well. Super duper useful. Right. Histograms. Right. I've been a bit flippant here, but I think I'm right. You can't beat a good histogram. If you've got data, then often the first thing you're going to do is, well, you want to see what it looks like as quickly as possible. So a histogram is a really good way of doing that, especially if you've made a repeated measurement over lots and lots of individuals. Okay, you get to see the distribution of that data. Okay, so to do that in R, it's dead straightforward. Box plot. No, so I get ahead of myself. What am I doing? Oh, histogram. Histogram, that's a function. Open the brackets. And what I'm going to do in here is I'm going to type the word. I'm just going to give it the column, right? So there's my cancer data subset. Let's look at the histogram for the radius values. Control and Enter. Couldn't find histogram. That's because it's late in the day and I'm getting tired, and it's just hist. Sorry, right? H-I-S-T. There you go. There it is. And of course, not acceptable under any circumstances without an appropriate label. X label equals tumor radius in microns. There you go. It's tried to give it a title. Not really a great title, but I could change that. Main equals histogram of tumor radius. Okay. Okay. Brilliant. Okay, so that gives you the frequency. So what this column represents here, this large one, is that in the range between, what's that? That's probably between something like 12 and 14 microns. There were actually over 150 tumours in that range. So the most common range of, most common size for these tumours is between, I don't know what that is, that's about 12 and 14 microns. Okay, that's useful. I could have called it on anything. It doesn't have to be radius. I could have done, what was it, fractal dimension. There it is. Okay, and I get another histogram. Okay, and what you generally see is you've got this kind of it looks like it might be a normal distribution, but it looks like it's kind of skewed. So I wouldn't say it was entirely normal. We'll talk about normal distributions in a short while. I've only got 20 minutes left, so I've got to be careful, right? But that's your box plot, okay? Oh no, I've done it in the wrong column. I've done it in the wrong boxes. Oh no, sorry, box plot. I'm getting confused between a box plot and histogram here, folks. Sorry. Right. The histogram's nice, but a box plot, even though it's kind of simpler in construction, is actually really, really useful when you're trying to compare groups of data. That's much harder to do with a histogram. If I was to compare two groups, say I wanted to divide this histogram into two groups, benign and malignant, they would probably overlap, and it wouldn't really be that easy to see what was going on. That's what a box plot is for, okay? So I can create a box plot really quickly using that column again. So cancer data subset, let's do radius again, okay? And it will give me a box plot, right? And what the black line here is telling me, that's the median. What the first line of the box is telling me, the top line of the box, that's the upper quartile range, so that's 75th percent. This is the 25th percent here, and I think this is kind of this is the upper range. I think that's like 95% or something like that, right? And here would be 5%. Everything above it, these circles, are what we call outliers. Okay, and the outliers are points which we deem, and actually R makes this decision on its own, as to measurements that it considers to be outside the distribution range. Okay, and you can actually turn these outliers on and off. I think you do it with outline. Let's have a look. If you type outline equals false, there you go. You can actually turn on and off the outliers. Okay, I'm going to leave them on for now. Now this isn't terribly useful, right? It tells me the median, but the histogram, I think, was probably telling me more useful information. The box plot really comes into its element when you're trying to compare multiple groups. So what I would like to do here is I would like to compare those two. I would like to compare the radius of tumours in the malignant and the benign groups. Okay, so I am going to again write box plot, and I'm going to this time do something slightly different. I'm going to check my notes because I always get a bit stuck at this point. Which is perfectly fine, by the way. If anyone thinks I walk around remembering any of these functions, then I don't, right? And you shouldn't either. That's what Google's for. But what I'm trying to do, let me have a look. Yeah, so I actually want to generate two side-by-side box plots according to those two groups. If I type the word radius, and I'm going to use a little squiggly hyphen, that's the tilde. On my keyboard it's shift and hash, depends on what keyboard you're using. If you're using a Mac, you'll be looking for it all day long, right? And I'm going to write radius diagnosis. I'm going to put a comma, and now again R has no idea what you're talking about at this point. These headers don't refer to anything until you say data equals cancer. Thank you, Chris, for that. I knew someone would jump in and defend the Mac users. Cancer data subset. Control, Shift, and 3 for Mac users. Brilliant. And then I'm going to press Control and Enter. Ta-da! Now that's useful, right? Let me tell you for why. Because I can see immediately there's something going on here. There is a significant, well, we'll figure out how significant it is in a second, but it looks like there is a sizable difference in the median value of the radius of tumours that are malignant compared to those that are benign, which is probably what you and I would expect, right? So, okay, that's really, really useful, and of course you could do that for all sorts of data, which is grouped and has measurements in. Let's dig a little bit deeper. let's have a look at another scatter plot. Okay, so sometimes it might not be obvious, but there may indeed be a relationship between two of your columns with measured data in. So, for example, you might compare the radius with the texture, or the radius with the fractal dimension. Okay, and you might get some correlation between those. So you've got to be very, very careful about cause and effect there. Is it the radius that generates an increase in fractal dimension, or is it an increase in fractal dimension that increases the radius? You've got to be very, very careful when you draw conclusions about correlations. But sometimes a scatter plot can tell you a lot. So let's just do a quick scatter plot here. Remember what that was? That was just simply plot. I'm going to do, let's do fractal dimension versus radius for data equals cancer data subset. See what happens, right? Okay. So it doesn't actually look like there's a lot going on there. You've got some outline. You've got some big ones up here. So generally, you might be able to say that the smaller the radius, the higher the fractal dimension. But of course, we've got this other factor in here where there's a big difference in the radius between those in the group that are malignant and those that are benign. Okay, so what I might want to do, and this is the funky bit, is I might actually want to colour those circles according to which group they're in. Now to do that, in R, I am going to, I'm forgetting how to do it now, I'm going to use the col parameter. Col means colour, and what I need to put in this parameter is a big list of values corresponding to every single point on that graph. Okay. Now if that point is malignant, I want it to be red. If it's benign, I want it to be green. Now to do that, I've got to remind myself because I've forgotten already. I do this. It's actually an if-else statement. Okay. And I open that because it's a function, and I'm going to use the handle diagnosis. And this is a conditional statement, right? So I'm going to use a double equals. So basically, if it's this if-else statement, it says if diagnosis in my column is equal to M for malignant, I want the circle to be red. Okay. Else, comma, I want it to be green. Right, let's run that. Okay, there you go. I've now got a graph. I'm not sure how easy that is to see online, but it's coloured all of the benign tumours in green and all of the malignant in red. So you can see there's like a big dividing line at about the 15 micron range, which determines whether they are malign or benign or malignant. Get my words confused. But because this line is sort of almost vertical, I'd say, with a bit of scatter, you might consider there to be very little dependence of fractal dimension on the radius. Okay. You could use any number of correlation tests to prove that. I'm not going to do that today. I just wanted to show you that you can colour your scatter plots and show useful information based on the grouping of your data. Okay. Right, so it's 10 to the hour. I think I've pretty much covered everything I wanted to cover apart from statistical tests. Right, so I'm going to whiz through this in 10 minutes. Right, but the last point, last thing I've really wanted to do is construct scroll up to the box plot. Here we go. The last thing I'm going to do is actually start to construct some hypotheses based on my data. So, for example, I might construct a hypothesis which went, there is a significant difference in the mean radius values of tumours between the benign and the malignant groups. Okay. So that would be my hypothesis. Okay. Now, typically when you're performing a statistical test in R, you don't test your hypothesis. You actually test a null hypothesis. So the null hypothesis is kind of the inverse of your hypothesis. So instead of saying there is a significant difference, my null hypothesis is there is no significant difference between the mean radii values between the benign and malignant groups. So that would be my null hypothesis. Okay. Now, in this scenario, the best way to test something like that, where you've got measurements across two different groups, is an independent t-test. Okay. Now, I've provided more information on the independent two-sample t-test here. You can go and read all that. I just want to show you how to do it. So, the first thing I need to do to test this null hypothesis, there is no significant difference between the mean radius values for malignant and benign tumours. First thing I want to do is I want to actually subset my data further into those two groups. Okay, so I'm going to create a data frame called benign. Okay, and I'm going to subset it. So it's cancer data subset. So I'm now creating a subset of a subset, right? And I call it again, and I hit the column diagnosis equals B. Okay, so what that's going to do, it's going to whiz through my data frame. It's going to pick out all of those rows that have a diagnosis equal to B for benign, and it's going to create a new data frame which is stored in this variable called benign. Okay, I want to do the same for malignant. Equals M for malign that time. Okay, if I typed it incorrectly, looks good to me. Control and enter. Right, I've now got those two subsets. Okay, now I'm going to run a t-test. Okay, and we'll worry about what comes out of that afterwards. So my t-test is simply going to be in R t.test. I'm going to put each of the radii columns from each of those subsets into here. So the first I'm going to put in is benign, column radius. Sorry if I'm going fast here, folks. I'm just conscious of the time. And then malignant, $, radius. Okay, you have to use the column values in this t-test. Control and enter. Okay. And it's performed a t-test. Now, it hasn't actually performed an independent t-test at all. It's performed, by default, what we call a Welsh two-sample t-test. Now, a Welsh t-test makes the assumption that the variance in each of those groups, variance, of course, is the standard deviation squared. It assumes that the variance of those two groups is not the same. Okay, in fact, it very rarely is. No one ever really does a true independent t-test. Okay, we're often doing a Welsh t-test, and what we've got here is a load of information. Okay, so it's given me the means of each groups. So the mean of the benign group was 12.14 microns for the radius, and the mean for the bigger one, for the malignant one, is 17. So you can see immediately the means are higher. And it's given us a t-value of minus 22.209. Now, if you had a table of t-values here versus the degrees of freedom, you could read out the p-value, but R has done it for us. R has actually calculated the p-value. What is the p-value, I hear you say? The p-value essentially is an indicator as to the probability that the difference between the means in those two data sets is by pure random chance. Okay, so if that p-value is like 1, it means there is the probability that the variation in those two groups is due to random chance is 1, which means there is no difference, there's no significant difference. Our p-value is like 2.2 times 10 to the minus 16. It's a tiny, tiny value. So it's basically telling us that the probability that the difference in these two means across the groups being due to chance is very, 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 very small. Very small indeed, okay? And actually what we do as scientists, in life sciences at least, if you're a physicist or an engineer, you might use a different threshold. But we say, right, if your p-value is less than 0.05, that's 5%, then we can assume that there is a significance. Something is generating a difference which is not due to random chance, okay? So in this case, we would actually reject our null hypothesis that there is no significant difference, and we would accept our original hypothesis that there is a significant difference between the mean radius values, okay? Now, I think that's the end of today. I've been a bit naughty here. I'm going to leave this up for the rest of you. I've been a bit naughty because you should only use an independent t-test on samples of data that adhere to a normal distribution. In other words, it looks like a bell curve, okay? Now, that's true, I think, of the benign group in this case, but not the malignant group. Now, because that is not true, we shouldn't really use a t-test. We should use what we call a non-parametric equivalent. And in this case, it's called a Mann-Whitney-Wilcox test. How you implement that in R is almost exactly the same. You just type, I think, wilcox.test instead of t-tests. Okay, and it just accounts for that non-normalcy of your data. I've also included here a bit of information on how you determine whether your data is normal. That's another statistical test called a Shapiro test. But I'm out of time, I'm afraid, folks. So so what I'm going to do here is I'm actually going to complete this document. Actually, no, I've got a completed document. So I'm going to send that all to you via email. You have a complete document forever as far as I'm concerned. I'll also include in that email a link to the live recording, which has been broadcasting, as I hope it has been, as we've been talking. So you can go back and watch that, or you can share it with your friends and talk about code. If you've got any questions, I think what I'll do is I'll stop recording and I'll stay in the chat for another 10 minutes. Chris, I hope you can hang around for another 10 minutes or so. If you've got any questions, then please just ask. Even if you just want to tell us what you'll do or what you hope to achieve by learning code, and that's it for me. This is why I do this, by the way. Is I know you're not going to go and look at maybe a breast cancer data set. You might be doing something with aerospace, or I think I saw transcriptomics or genomics or something else. So I really am interested in what you intend to apply this knowledge to. That makes it really exciting for me, so thank you. If you really want to test your knowledge, I've put in a couple of questions at the end on another data set. Now this is a really famous data set. Well, infamous, I should say. It's based on the passenger data that was recorded after the sinking of the Titanic. Okay, it's a bit morbid, but as a data set, it's quite a well-known data set for anyone who's looking for an introduction into data science. Everything we've done today, you can apply to that data set. So you can go and plot a box plot to show whether there's a difference in the median fares, I should say, between those groups that survived and of course, the ones who had more money survived. Surprise, surprise, had a bigger probability of survival. So you can go and apply everything you've learned today using that data set. If you've got any more data sets you're interested in, or think, I would really like to do this for this data set, get in touch. You can always get in touch with me. My email, I should put it somewhere. I'll put it in the chat here. It's r.treharne@liverpool.ac.uk. So please do send us a line if you're interested. I'm going to stop the recording now. I'm going to stop the YouTube now. And then, there you go, that's stopped.